Yo yo yo, sorry about the slow start today. Things doesn't really want to cooperate with me today. And I also noticed that my usual go-to for music during streams, shout out Chill Hop, is currently under maintenance. So yeah, we're gonna do a no background music today. Okay, let's see. Hopefully, the development itself will go fine today. So I'm just going to start with checking where we're at, and I think we have a pretty good, very basic fluid solver in place currently, but it has some shortcomings. And yeah, let's just see if it still works. So I'm just gonna maybe like that, and water. Oh yeah, because we need to do... So currently my environment has a fluid solver component, and here we can choose the mode for the fluid solver. For default is none, which we want to change to naive CPU, I think. And if we add 0.2, what kind of water do we get there? It's okay. 0.3. I'm a little bit worried about the small variations we can see. Not entirely sure how exactly I want to handle them. Is 0.4 too much? Yeah, it is. I wanted to highlight one of the other shortcomings as well. So the small variations in water, we can probably fix that by truncation, I would guess. So let's go minus 0.5 here. And then maybe we can do 0.5. Something like that, maybe. .4, is that too much? Yeah, we're gonna try and work with some dispersion here, I think. The question is... This is rough. Definitely. And this is sorta rough. And I wonder... We could add some very basic costs to this fill algorithm, and I think we might see some instant improvements. So this one actually holds more water than this one, but the terrain here is a little bit higher up, and that's why this one is lower. So I'm thinking... And and all of these has the same amount of water, but the terrain here is lower, hence we get this. And if this would have just stopped around here, it would be sort of fine. So you have a pool of water leading to a little bit of a, I wouldn't really call it a waterfall, but something like it. And then you don't really have enough water here to get a pool here. But I don't know. I think I need to put the pen to the paper and write some of these constraints. Like, we want the water amount. Here we have a lot of water. And when we go over this edge here, we want the water amount to decrease. Would also love to avoid... Yeah, so like in this case we want it to decrease. We want it to decrease in this case as well, but in another way, I would say. And local minima like this, I don't know. Yeah, we're gonna do some experimenting. Hopefully we can... I don't know what one exactly would do with this one though. Yeah, it's rough. But... then again, one could probably... Like, my initial idea was to take the center point of each of these water elements and recreate a mesh out of it. But... if we just take the outer edges and create meshes out of those, this would lead to a pretty good object, I think. Still worried about this one though. Is that too much? Maybe it is. Yeah, probably. Good morning, Harukanan. What's up, Crypto Fighter? Hi, are you making some sort of fluid object that the player can place? Yes, indeed we are. Pretty early in the development of it. Zero 0.4, is that too much? 0.3. It's definitely rough. And I've been thinking about placing some cost for the fluid to move upwards. I don't think we have one right now. But the question is, I still wonder if this one doesn't move upwards here. And if we move upwards, or if we add a cost to it, we're going to lose this one. Or filling out just a lake like that. One could think as well, like, so this is one. It's a single iteration basically. But one could think that we generate this, and when we get to a stable state, we reiterate it and figure out some stuff. I don't know. What if instead the player places a cube which keeps getting bigger horizontally, vertically if there's space below, and use a shader to make it look like fluid? Oh yeah. Like, what we're developing here is just the back end of the fluid solver. Like, we're given these data points, when we reach a stable state, we're going to convert it into a mesh and add some nice water shaders to it. This is just like trying to figure out a simple, very specific algorithm for filling out varying terrain with water, basically, and also creating like pools of water and rivers, connecting them and stuff like that. So yeah, we're far away from trying to think about the visuals as of this point. Oh, looks like a fish, so halfway there. Sorta. What's up, Smack? Fuck, when I see this, I'm basically just wondering if we want to implement Joe Stam's fluid solver. But it will achieve stable states that are insufficient for what we want to use it for. So I wonder. Oh, congratulations, Smack. Feel free to link it if you want. Is it the inventory asset? Nice. Saving that link. Gonna check it out after the stream. Have you gotten any nice feedback yet? We have, when it comes to this fluid solver, we have a constraint, or we have two constraints that sorta works against each other, I would say. Like, we want to get rid of this. We don't want a local minima like this. But we still want fluid to be able to go over a ridge and go down. Oh, that's still nice. Or, like, could we use this current solution as just a initial terrain check? Like, basically we fill out this given the current rules we have, and then we loop through and find the edge ones, and we add some additional information to those. And I want to do something with that. If we just had the edge ones here, would it be too bad? We still have some. Maybe it wouldn't be too bad. Hmm. Yeah, the overflowing is bad, but if we could... Like if we would have gotten... I definitely don't want to... Get a pool of water, unfortunately with a local minima, which sucks. But if we just take the outer ones... It should be pretty okay. Do I want to do that? What material do we have here? We have... Base map. Is that... Is it called albedo? Like, okay, apart from the overflow, if we just take the outer ones and recreate a mesh from that, and then we get a little bit of a waterfall here. We get... We get a little pool of water here with varying heights on the sides. Yeah, that's not good. It's not enough. Oops. Yeah, the problem comes when we're reducing the amount of water. Pretty much. It's not good enough. What's up, Yucca-Pekka? I love the name. The problem is a lot of things. We're basically in the process of very early in the process of implementing a fluid solver with a set of given constraints that will make it possible for the character to add water to this terrain. And we have a very naive, extremely naive implementation or first iteration of a fluid solver, which in some cases it works good, in most it does not. It's rough. Get overflow, yes we do. I wonder, like, maybe I'm a bit too optimistic, but if we take our extremely simple fluid solver and introduces a variable cost, fuck, how would that look? Like, we introduces a set of costs for instance, for walking upwards. Nah, that won't solve that issue. First of all, the most basic cost we introduce would be steps from initial spawn point, right? Yeah, it's pretty damn rough, Yuka. But yeah, like it's a good start. It's a good start. And like when it comes to like my experience with fluid solvers is, yeah, I haven't really done that much with it. I've done some Joe Stam stuff way back when. So this is going to be a learning experience as well. So yeah, it's a good start. Hopefully we can get somewhere meaningful from this. But I wonder if do I want to... Yeah, I wonder if we're gonna introduce... Like, if I just draw some terrain in, I don't know, some image editor, and we load them at start. That way we can draw some scenarios we want to try with this one. Yeah, maybe. What is the... let's see here. Environment, what do we run with? Resolution 256 and a subdivision constant of 1. Yeah, we know that... Yeah, we might subdivide it. So if we create a texture that is 256 times 256, and then we can draw some terrain on that one, some rivers and pools of water without any water, and then we just... Yeah, that will save a lot of time, and we can... It's easier to design the actual scenarios. Shouldn't be too much. Let's see here. Environment, terrain, base. Yeah. What do we have? Terrain data, terrain test data. Yeah, we want something like this, but... Debug material. Initial terrain data. Probably want that as an array, and then we do a subdivision. We create a new, and then we generate terrain data. We have a noise scale here. Do we have any more of these? No, we don't. So let's just do public void generate terrain data. And here we have one. Let's see here. Width height, we call this one. So what do we do here? We do height range, we do that here as well. Then we generate these. Okay, beautiful. I think we have it in place. And then let's do we don't use this one anymore. Was it this one? Yes. Okay, so terrain data is equal to new terrain data. We want resolution, height range, and then we're just going to send in initial yeah, let's do this one as well. And then in terrain base, we just check generate terrain data, and we're gonna check here if dot length. We're gonna check if what is it? I times subdivision plus j is less than initial terrain data dot length. If so, do this, else do this. And here we do yeah, so as long as we have textures in this one, use those. Otherwise, use this one. Although I wonder... yeah, it should work. probably the same method we are going to use later down the road when we start working with persistence. Okay, so no errors for this one. Let's just try environment. What do we have? 256. Do I have any 256? No, I don't. Let's create one real quick. What do we have here? Environment textures, terraform brush, terrain, data, noise. Let's delete this one and terraform brushes. And then we add terrain test, or just terrain textures. And I need to keep in mind red height, G grass, B water, and alpha unused so far. So we're gonna do, what did I say, 256. So full black with an alpha of 1 though, but that's okay. And then if I want to draw height here, we want to do it with red, and we can I just want to try this one first of all, see if our loading system works. Yeah, let's try this. Terrain texture. Yeah, terrain texture test 00. And we want to make sure that it's default, non-sRGB. And is there anything else? No MIP maps and point filtering. And that's about it, I think. And then if we go initial terrain data and we add one element here, we add this one, and let's see how it looks. Okay, that's good. Is it a bit far off? Maybe not. Very rough. Yeah, maybe we want to do bilinear. I don't know if it will fix it or not. That's extremely rough. But it's okay, it's okay. So what would... Can we do... Yeah, we can work with only red. And then if we add green and blue... Okay, so we work in all of them. Oh, that's not good. Okay, beautiful. So we do this, and then we do this, and now it's only red. Yeah, nice. So we're gonna do this, and then... Okay, we can do this. So what am I thinking here? I'm thinking something like... Actually, let's do... Every stamp has its own opacity. Do we have alpha in this image? Okay, so now we have alpha, but we can't really... Okay. Incremental. Every stamp has its own opacity. There we have opacity now. Okay, there we go. 20. Okay, beautiful. So what do I want to do? But that's not really what we want to do, I don't think. Maybe. Yeah. And this is extremely big as well, but so what do we have? A very big pool, and then we have, if I only show red here, actually we do. Yeah, getting these, okay, yeah, that sucks. Getting these to an acceptable state is probably gonna take longer than I would like. Okay, so do we only remove opacity? That's weird. Yeah, that doesn't work. Honestly, let's just do it extremely simple. Let's do it like this. No need to overcomplicate stuff just yet. 256, 256. And we do only red. And then we do a box like that, and then here we do a little bit of a, I don't know, 0.8 maybe. What is that? 200 maybe. That's not that much. 50. Let's do 50, 50. So we have a little bit of a 50, 50, 50. And then we go and do so that's 50, 50. Let's go with a, fuck, am I working with two small values? Maybe I am. We'll see. 30, 30, and then we do zero. Yeah, this is gonna look, it's gonna look like shit, I think, but hopefully we can try some things. So basically, like, if we fill up this one to the edge and then we get to this one and we will reduce the water amount, it will flow down here, down to this pool. This should be like maybe one of the more basic stuff that the water system should fix. and also a very good example of how we want this fluid solver to break real world physics. Like, I've said it multiple times, but if we don't have a constant influx of water here and a constant outflux of water here, this river will be empty, right? And we will just get a pool of water and a pool of water. Like, we will fill this one up, it will overflow and end up here. What's up, Ayland? So let's see, and now we have this texture. Let's take a look at how it will look in game. I'm wondering if my height values might be... There we go. Okay, that's pretty big. But also, I notice, yeah, I went with way too small values, I think. 30, does that just yield... That's a very small bump. Oh yeah, one thing we might want to do, no sRGB, we don't care about MIP maps. Do we have a bigger difference now? Hopefully. Fuck, it's way too big. Yeah, there we go. And then we have a small... It's too small still. Yeah, I don't need to... We don't need to go overboard. But it's actually... It's not that many pixels. But let's see. Okay. So 256 pixels. Let's do... We're gonna do show grid. I wonder if we can do snap to grid. I have to remember that this is extremely big, so let's do... Bit of 100. Fifty, 50, 50. And 0. Yeah, we can just work with small systems like this. No need to go overboard. There we go. Everything is set up correctly. Okay, let's see. Given the height difference we have on the terrain, this is probably gonna look pretty rough, but I think this will work as the initial test scene. It's very rough. And then we do sRGB here. I wonder why. Okay, so we get down to here. I wonder why we're getting a bump here. That's weird. What is with this bump? Yeah, I need to fix a custom camera for the water as well, but yeah, let's just 0.34. Then we get a nice downflow, and then we get to the bump, which I thought we wouldn't have. But then we stop. Yeah, and if we recreate a mesh out of this, it would look pretty good, I think. Tiny waterfall, bigger waterfall, down to a very small puddle of water. So yeah, this very naive approach works here. But this is pretty much a test case specifically made for the current implementation, I would say. And I don't want to have this much of a difference. Environment. Height range 0 and 3. It's not that much, but 0 and 1. Will that work better with? This bump over here. Oh, do we still have? Oh yeah, I know what's wrong. Yeah, okay, I get it. Yeah, we're not reading the middle of the pixels. Or are we? No, we're not. Okay, so let's do this. I don't want to focus on that this stream, so we're gonna go. It actually has to do with, let's see here. When we read, when we do terrain data container, when we create this once here, set terrain data, then we do a blit, new data, data as render texture. This new data here, we need to add a custom shader here as well, I think. That sucks. Because we need to scale and offset data as render texture. Or we need to scale and offset new data, I think it is. But I wonder. Can we use Terraform brush texture? Terraform brush material. Could probably use this material. But we should be able to use. We're still gonna need to send in the material here. Not too keen on that. Do we have shaders? Terraform shader. I think we're going to write a new one. And it's also going to be a functional shader. Let's just copy this one. Terrain load shader. Brush texture. We want to write to all. We don't brush operation. We don't want to blend. We don't want to do a color mask. We don't want to do a operation. So I think we're just going to do this. Remove this. We need brush texture, but we're going to rename it. And then we need to have some scale settings here and stuff like that. Test scale, test offset. think we need no header. I think we're just gonna do these as floats. And I've done this so many times right now, so we should be able to just grab one of our we should be able to grab terrain debug shader. And what do we have here? We have terrain data texture. Fuck, let's terrain data UVs, yes. So we pretty much just want replace this with this terrain data texture. Ugh. Here we just need to do this. But I forgot. Okay, so we're gonna do this from a blit, and when we do it as a blit, I think we need to call this main text. Pretty sure. So when we do blit, the first argument is going to be set to the main text, and the second argument is going to be the output texture. So let's rename this one and this one. And then let's see, we don't need this method, and there's a lot of things we don't need here, but we do need this and this one. Position object space UV. We're going to rely on this one as well. Position clip space UV. That's all we need. Position clip space output UV is equal to input UV. Nice. And then we rename this one. Just UV, I think. Multiply by scale, add offset, and then we sample the main texture using this sampler. And I think we might as well do return here. Am I missing something? I'm just gonna double check the blit. Pass the source to math material as main text. Okay. So the idea then is in terrain data container, when we do set terrain data, do we use this one? It's only here. Terrain data container, new data, and then we're gonna have material New data as source, data as render texture, then we read it back. And then we need to send in. Okay, so all that's left now, if I don't have any compiler errors, is that we need to create this one and we need to send it onwards. And we also need to set a few things here. So, and that is in terrain base, and we're going to have initial terrain data. Terrain data load material. Probably going to rename that one. So if we get into this one, this is, we want to have this one here, but we need to set a few things here, and it is terrain data text to UV scale, terrain data text to UV offset. Let's just rename these, and then we can use the same constants. So if we load this one, and now we're going to set these multiple times depending on how many shaders we have or how many initial textures we have. Am I okay with that? I'm pretty sure we want to use the same values. As these two. Pretty sure. But now we're tied to a resolution here. Wonder if this is all we need to do. What's up, Trippin' Murphy? Okay, what is the problem here? Yeah, we forgot a equal to. Anything else? Yes. This one is old, I think. Let's try it. Let's just run and see what happens. That is rough, and I know why. Because environment, we need to define the material. Here. Functional material. But I'm a little bit... let's try it. Hopefully, we still have the bump. That's not good. Did I screw up my... Actually, it looks to be correct. Let's see. Yeah, we have 4 times 4. Yeah, it looks to be correct, but I'm still perplexed by this second bump we're getting here. That one is weird. Can you tell us what specifically you're working on right now? Right now we're trying to implement fluid terraforming. So right now we can terraform the terrain, I thought. Oh yeah, we need to do this. We can terraform the terrain. And we can add grass and stuff. But now I want to introduce water, and that is quite hard. So we're working on a very simple fluid solver right now. I still think we're getting a little bit weird results when we're reading this texture. Y. $50, $50. Point, no MIP maps. Linear color. Looks great so far. Thank you, appreciate it. Yeah, the only thing I can think here is that we're reading the wrong pixels, but we're using point no filter, so we would either get this or this color. Unless... I wonder if... Yeah, there we go. Okay, a compression issue. Good to know. And if we add 1, we get this water. If we add 2, 3, 4, Okay, so in this case it works. And if we add 6, yeah, this is pretty much the only case where it works, I would say. And if we add 7, yeah, this is how it's going to keep working. So let's add some other test cases. And then of course, if we add 1 up there as well, we're gonna get this forever. Yeah. I just need to figure out what kind of step size do I want to use. I would water brush at 0 to 1 with a step size of 0.1. So we get, what is it? Is it 11 different levels? And do I want to count 0? Yes, I do. Or actually it's 10 steps. So 255, yeah, 25, 25.5. Yeah. Okay, so let's go. Zero 0.5. Yeah, 0.5 times 256. 128. Yeah. Let's do. Oh, this is gonna look extremely ugly. Let's do this. And let's go. Zero 0.4 times 256. Zero 0.3. Or do we want to do? Yeah, let's just go. What did we have? 128. 8, 16, 32. Oops. 96. 64. $32. And 0. So I wanted to be able to handle something like this, but we're probably going to see a lot of weird stuff going on. Actually, I'm going to save this one as well. The difference between them are... Not that great, but it's okay. Oh, it works so fucking good for simple test cases like this. What a beautiful water flow this would be. Too easy, too easy. I want to try... Yeah, it should work pretty decently the other way around as well. I wonder how the fluid solver would work with if we introduce priority as well, very related to costs. But for instance, if it always choose the next cell with the lowest cost, and we can base the cost on height difference first of all. So it always choose the one that won't work. Or will it? No. It will work. In this case it will work if we always choose the neighbor with the lowest height. But for instance, in this example, when we have a little bit of an uptick, it will fail. I'm starting to ponder if I should just implement Joestam fluid solver and see if we can constrain it, if that might be an easier approach. But okay, so I want to do, let's see here. Let's do a similar test as this one, but with, what do we have, 16, 14, 8 times 8 might be a little bit too small. 16 times 16. Okay, that's more like it. Because I think the current solution is going to start breaking right about this setup, I think. But watching this, like, we should be able to clean this up. This would look pretty good, I think. Yeah, it would. This gives me hope. But it's still a pretty basic setup, I would say. Then we have this case. So when the overflow here gets too big, it will continue walking like this and then go down, and that's up. Maybe it's not too bad. Yeah, we get these local minimas which I want to get rid of. But like this looks very good, I would say. Get some flows here. Maybe it's not too bad. But we want to do some more examples, worse ones. So what if we did? Yeah, we have one more problem as well, I think. And that would be I'm wondering if we want to do some a preface of this. Like, for instance, if we add now it becomes a question of gameplay as well, because like if we add a tiny bit of water here, then we get something like this. Gameplay wise, that's not something we want to end up with, so I wonder if the first thing we want to do is to find the minima, the lowest height that we can reach, because that is where most of the water will end up. So in this case we would probably find this one. Is that a better solution? Or will it improve stuff? Like if we find the local minima or the lowest point, and then we get how much water that one will hold with this very naive approach. And then We walk backwards. Would that solve it? It would basically just solve the issue of getting something like this. Good morning, Dasai. It also feels like one very easy approach would be so like this is the initial phase, right? And then we just add an additional iteration phase on this one, which averages values. So for each water we have here, we average a cell's value to its neighboring, to its neighbors. And then we're getting closer to a real fluid solver. But that would probably solve a few of these issues, I would say. So we take this pixel and then we average it with the neighbors. And what we get then is, so we have zero fluid here. We get less fluid here. We're going to get more fluid here, and we do that until we're in a stable state, which we define in some way. Like this is a very feels kind of a hacky approach, you know. So in the case of good morning, GK. In the case of adding water like this, we would probably get a lot more averaging. I wonder if we would eventually get a good result. The good thing with this step is that it would be perfect for the GPU. Would we get or averaging it might I don't know. Finding the local minima feels like the way to do it when it comes to stuff like, I can't really show it here, but stuff like this. Averaging the fluid surface height. Maybe. Why not? Might as well. It shouldn't be too hard. Averaging the surface height. So what do we want to do? We want to check the surface height of neighbors. But we also want to take fluid amount into account. I want to try something with that, I think. Or better yet, I wonder. If we want to try something like, oh, fuck, this might be if we apply let's see, if we apply water somewhere, we do initial pass where we find the local minimas. So I guess that is cells that don't have cells that has an equal height or less than all of its neighbors. So we find those points, and we should be getting 1 point here, and maybe 1 point here, maybe 1 point here, and here. Right. And then if we find those points, then we use some A-path algorithm. So we take the cell from all of the local minimas, we take the cell that is closest to the influx of water. We add the influx of water to that point, and then we walk to the other minimas. And we have, when we travel, we also have some costs and stuff like that. So when we get to a local minima, we know how much water should be there. And that's when we fill it up. A solution like that would work if we take a look at this one. Here we have multiple local minimas, but it doesn't like, so I guess we will get all of these. So we will traverse to all of them. Sure, it's performance heavy, but I don't think it will fuck with the solution, because let's say that we add water here, we get these local minimas, we get these local minimas. So then we walk from this one to this, but yeah, the cost to walking to this one will be 0. It's a little bit of a distance, but it's no height difference. We can work around that. But locating the local minimas might actually be a very good idea. I wonder... Like, given the constraints we have on this water system, I think that's it. But it can still lead to some weird stuff, can it? So for instance, if we would have something like I don't know. No, I think it's okay. Because, yeah, if we find the local minimas, and then we calculate how much water reaches those local minimas, and then we add that much water to all the minimas. I don't know. And then we use this naive step algorithm to fill them all up. Yeah, won't really lead to nice rivers. Too bad. But I still wonder if we can make some... So given that algorithm, we would end up with a set of local minimas, and we will get the cheapest path from the influx of water to each of those. And I wonder... If given that data, could we recreate some nice water? I want to try it. Definitely. And we're always gonna choose the cheapest path, which means, yeah. Okay. So finding the local minimas, drawing cheapest paths to them, then we know how much water will be at each minima. And then we walk through that path, and for each element in the path, we fill neighboring pixels that has a greater height than that one. With as much water we have in that. I see a few problems, but this could very well be one solution. What do we have? Basic, iteration 1 CPU. Let's call this one naive recursive CPU. Yeah, we're gonna rewrite this one in a better format here later on. Local minima. Local minima connection. Yeah, that's a cool name. So given an influx of water at position, I just want to do the steps first of all. Although we have to give a initial it's pretty much going to be something like this. Find all elements. Is that the term I want to use for them? Find all points. Let's go with points. That has a height that is less than initial water, or actually we're going to do height. I want to do P0. So find all points. That has a height that is less than height of P0 plus water at P0. So we add an influx to a point, and the first thing we do is that we take the height of that point, we add the water amount to it, so we get surface height. Let's do I don't know what I want to name that one, but okay. And then find all points. Can we do from, actually we do it as a set. So find all points, big P. From P, find all points that has a height. Find all points that has a height that is less than all of its neighbors. That should be pretty straightforward, I think. Yo, what's up, DevSpiers? Thank you for the raid, and thank you. And welcome to all the new viewers. We're just trying to... How should I put this in words without appearing insane? We're trying to figure out a custom fluid solver algorithm, and it needs to be very specific for our specific use case. So it has a lot of rules, which means that I can't use like a go-to fluid solver that exists. Or that is my understanding right now. Maybe we will... There still exists a small probability that we will end up with a already made fluid solver, but that's okay. Okay, from P, find all points. What do we want to call this one? I'm going to call them M for minimas. Optional step, I want to do remove. This is what's, if we can make this, remove all duplicates. So here, remove all duplicates from M. And what I mean by that is, if we take a look at this one, if we take a look at this one, for instance, we can, let's render the height values. We can see here that we're gonna get a lot of minimas here, right? So this one, which makes me want to clarify this one, that has a height that is less than or the same as all of its neighbors. So we will get a lot of minimas here, which are actually the same minimas. And I wonder, and when I say remove duplicates, we need to remove them so we just have one left. And I wonder if if the best approach would be to take the middle one, or the one closest to the influx of water. That's what I'm wondering. So for this one we would do we want to take this one, or do we want to take this one? It's going to be a little bit, if we take this one, if we take this one, ooh, this one is rough as well. What's up, Andrews? New here. What game is this? It's a game in progress. Which is going to feature a lot of terraforming. So this one would be the minima here. It's like it's probably easier in this case. Would we have a minima here? I don't think we would have a minima here. We would have a minima here and here, I think. We're going to implement a minima algorithm, and then we can work from there. But like, this is one of the biggest problems we need to solve. How to handle multiple minimas like this. When we do... Yeah, because eventually... I think it's okay. I don't think it... I wonder if it matters what minima we pick. So when we have a group like this, I don't think it matters which one we pick. Initially, however, we're gonna have a lot of... We're gonna do a lot of computations which we eventually don't need. But like this... I think this might work. Think about this. So we get, let's say that we get a minima here, and we get a minima here, and the influx of water is here. So we walk the cheapest path to this one. Then we know how much water amount we have left. So this one will have that much water amount. And then we walk down here, down here, down here. We find the next minima here. The cheapest path gives us how much water we will have there. So we add that much water here. Spread it. And then we add... Or actually we don't. We wait with that one. But then what we do is we walk from this path, and or we start with this minima. Yeah, okay, so we need to find the closest minima, the cheapest minima. That is going to be our new influx of water. So we change it from here to here. Given the algorithm we have used to walk through this, we know how much water amount will be here. So we add that much water amount here. And then and then we walk through the path, then we walk through the path, and for each index in the path we have a new water amount for that index, and we add that water amount to every neighbor that has less Yeah, we're gonna have to choose in some way there. I need to think about that one a bit more, however. But I think with the information, with local minimas and the cheapest path, I think we can do some very nice things. And what's up, Cooler SK, by the way? Yeah, something like that. It all comes down to how we chose to... here's the red wasteland again. how we chose to utilize the data we get. But. Yeah, so for each point along the path, we want to add, if the neighboring node has a higher height value, we want to add this water value to it. So we want to set it to the same surface value. If it has less, that's when we revert back to the path finding data we have. And then we do that. Oh, I think this might work. Although I wonder... Yep, it might actually work. I'm pretty sure we're going to run into a lot of problems along the way, but... At an initial stage like this, I have higher hopes of that one yielding good results as opposed to this one. Elon, I'm creating a random system generator for my project. What kind of systems? So yeah, remove all duplicated. I'm gonna put this one as optional, or am I? Yeah, because it doesn't really matter. Optional for performance gain. And when we have all of those, use, probably gonna go with A star to find the cheapest path to all M. Pick the M. Pick the M from with the smallest or cheapest cost. That is the new P. Can we do P0? For each point in, and I wonder, my next question is, when we have the starting point, do we want to calculate the cheapest path from... find the cheapest path to all m paths. What do I want to call this one? And then we're going to say find the cheapest paths to all m, and then we pick this one, and for each, and then we're going to do like what I'm wondering, now we're just gonna do use pathfinding algorithm to find the closest m based on cost. Finding. Pick the m from m, or actually, then we have the m. And this is where we're going to get to the next stage, I think. So we find the closest m, and then we do fill all neighbors fluid amount based on fluid amount at m. I'm gonna have, yeah, fill all neighbors that has a greater height than m with fluid amount based on fluid amount at m. Yes. Fuck, will this work? Yeah. We're gonna do walk through the path to the next walk through the path to the next minima. Does this make any sense? Fill all neighbors of P, walk through the path, walk through the points, making up the path to the next minima. fill all neighbors of P in that has a greater height than P based on fluid amount at P. I guess that's all we want to do. For every m apart from D. Find the closest, let's see here. Find the closest M to based on cost related to. I'm gonna have to rewrite this, but what I want to say here is P0. Does this make any sense? Find all points P that has a height that is less than HV P0. So that is height plus water amount for P0. From P, find all points M that has a height that is less than or the same as all of its neighbors. So that's our minimus. Optional for performance gain, let's skip. Use pathfinding algorithm to find the closest M from M based on cost related to P0. So we want to find the closest minima. So we want, it's basically going to be, given our pathfinding algorithm, it's basically going to be the minima that is cheapest to reach given our initial influx of water. And when we have that one, then we use a pathfinding algorithm to find the closest m from m, so the next minima. So then we're going to start walking from minima to minima, but when we have found that path, the cheapest one, then we want to walk through those points, and for each point we want to fill all the neighbors that has a greater height than the current point. So our path finding algorithm is basically going to leave us with a path which for each point we have the water amount, and we're just going to spread that water amount, but we just do it to neighboring pixels or neighboring points that has a height that is greater than the one we're currently in. Because if we find one that has less height, we're gonna fill that one on from the next step in the pathfinding algorithm, I think. Yeah, and then when we get to the next minimum, then we just do that. But I do wonder. And we want to find. Yeah, and we want to do that until we run out of minimas or we run out of cost, basically. So we might end up at a point. Yeah, I think that's okay. Like the pathfinding algorithm and what we chose to define as cost and stuff like that is gonna carry most. Like all of this is going to depend on however we implement that one. But I think this is a pretty nice defined, cleanly defined steps. We can do this pretty easily. Yeah, I think we can do this. And I'm gonna start to implement this tomorrow, because let's see. Yeah, because unfortunately I won't have more time today. But it feels great to have this, although maybe not the best definition, but it feels great to have it as a defined as a step like this, and it's going to be easy to just start implementing this tomorrow. And right off the bat, I think I have higher hopes for this one than I had before we started implementing this one. So yeah. But okay, so this is what I'm gonna be doing tomorrow, because now I gotta run. But as always, thank you so much for watching, everybody, and have a great rest of the day. Peace.